All right, so just a few hints for our homework number 10. Remember that is only A, B, and C for number 33, A, B, and C for number 34, number 36, and then 838 part A only. So let's look at 833, A, B, and C. So you have an ice cream parlor with 28 different flavors, not quite 31, close enough. And with 28 flavors to choose from, how many ways are there to order a cone with 2 scoops if you care about the order of the flavors? So that's the only thing that matters, is that we care about the order. So in other words, what that means is that mint chocolate chip vanilla is different than vanilla mint chocolate chip, or chocolate chip is different than chocolate chip chocolate. We're going to count those as different things. It doesn't restrict. You can have the same thing. You can have mint chocolate chip, mint chocolate chip. You can have vanilla, vanilla. You can have chocolate, chocolate. And so what that means is we're going to use the multiplication counting principle. We don't have any of the restrictions. So how many possible do we have for the first scoop? How many for the second scoop? If we can repeat, we can have whatever this is twice. Orange sherbet, orange sherbet. Okay, and that would simply be 28 and 28. So 784 possible ways. Now where it gets a little bit trickier is part B. What if we care about the order of the flavors, but we have to have different flavors? We cannot have mint chocolate chip, mint chocolate chip. We have to have mint chocolate chip vanilla or mint chocolate chip chocolate. How is that going to be different if the order matters? And so remember what that is. That can call for, you can use the multiplication counting principle, or you can use our permutations formula. So for the multiplication counting principle, we have 28 for the first scoop, but then you imagine we eliminate one of them, you have only 27 left for the second scoop. So it's 756 possible ways. Or we can use the permutations formula where we say from 28, we are picking 2 where order matters, 756. And again, what was the formula? Let's take a look. And so I tried to print out some sample ones, but again, it's 28p2 is 28 factorial over 28 minus 2 factorial, or 26 factorial. And so what we see here is that you have 28, 27, 26 factorial, the 26 and 26 factorial, and the 26 factorial cancel out, and we'll have 28 times 27, which is exactly what we had here. Remember, the big difference between permutations and combinations is order matters. So for example, something like chocolate chip is different than chocolate chip chocolate. Or chocolate coffee is different than coffee chocolate. We're counting those separately. Order matters. If you actually list out the entire sample space, there would be 756 of these. All right, part C, a cup with 2 scoops of different flavors. This time order doesn't matter. What that means is that mint chocolate chip vanilla, I'm going to count that the same as vanilla mint chocolate chip. And so in fact, we're not even going to think of it this way. The multiplication counting principle doesn't work too well with this method. So instead, think about which is the way that we use where order doesn't matter. And hopefully you remember that's combinations. Combinations. So it's 28 from 28, C2. I'm picking 2 where order doesn't matter. Where do we get that 378? And remember, what's the difference? So the formula again is 28C2, 28 factorial on the top, just like permutations, over 28 minus 2, which is 26 factorial. The key difference, though, is we have this extra 2 factorial. What was that there for again? It's because you're overcounting. So remember the other one, we had chocolate chip, and then chocolate chip chocolate in the permutations. Let me just jump back there real fast. Permutations, we counted chocolate chip, and chocolate chip chocolate as 2 different things. Here, I'm only going to count that as one thing. Or we counted for permutations, chocolate coffee and coffee chocolate as 2 different things. Combinations, I'm only going to count that as one thing. So I need to divide by this overcount factor. So we're always going to divide by this number factorial. And so we get half as many, 378 possibilities. So note that this 834 is very similar. Just kind of apply those techniques for 834. All right, 836, I'm not going to do part A for you. But you pay $1, and it says you're going to choose a 4-digit winning number at random, a 4-digit number at random, and you get $5,000 if your number is chosen. So assume that order matters, and what's the chance you win? I want to answer this one though. What's the expected value? Okay, so what was expected value again? It's what's the average thing you can expect to earn in the long run? How do we find that? It's basically you find all the possible values you can get. Sometimes there's many different possible values, sometimes only a few, times the probability that that value happens. So, and you sum them all up, and that will give you your expected value. So in this case, there's only 2 possibilities. You can either win $5,000 or you can not win anything. Now remember, you're paying $1, so there's a couple ways you can do it. Actually, I realize this is wrong. So if you win $5,000, you paid $1. So actually, we should call that $4,999. What's the chance that you win? Again, that's what you're calculating. And then -1, you lose $1. What's the chance you lose $1? And then, again, you have a big weight over here, but your probability is really small. And here it's barely any loss, but there's a high chance you're going to lose. So altogether, do you expect to win a little bit of money, or do you expect to lose a little bit of money each time you play the game in the long run? Finally, the last one, the Big Slick Texas Hold'em problem. 2 cards and 1 strong starting hand is called the Big Slick, which is an ace and a king. Not necessarily the same suit. What is the probability of getting a Big Slick if you deal 2 cards? And so remember, what that is saying is, probably the Big Slick is, for your denominator, what's the number of ways to draw 2 cards from 52 overall? Again, with cards, order does not matter, right? If you get ace of clubs and 2 of clubs, that's the same as getting 2 of clubs, ace of clubs, right? 7 and king is the same as king and 7. So think about, do we use permutations or combinations? And then on top, in the numerator, what are the number of ways to draw an ace? What are the number of ways to draw a king? And we're going to multiply those together. Okay, if you forgot, we actually did a problem in the previous example, the notes, very similar to this. So just as a quick reminder, if you drew 5 cards, this is 5 instead of 2, and what's your chance of getting 3 clubs and 2 diamonds? So we did something very similar, just to remind you. So this time, what was the number of 5 card hands possible in the denominator? And what's the number of ways to draw 3 clubs and 2 diamonds, excuse me. And so again, the denominator is 52C5 because we're drawing 5 from 52. And the numerator, 13C3 because there's 13 clubs. I'm picking 3 of them. And there's 13 diamonds and I'm picking 2 of them. We multiply that together. Okay, and so it was a crazy small probability, but this is very similar to what you do for this one. Key differences again is we're only drawing 2 cards. We're only looking for 1 ace and we're looking for 1 king. Okay, so with that, those are your hints. Good luck.